Hey guys, welcome to part 2 of Exponential Functions 5.4. So let's continue with our next examples. Now I have a product of e to the x and tangent x, so I must use the product rule. First term times the derivative of the second term plus the second term times the derivative of the first. So e to the x tangent x plus secant squared x. Okay, now sometimes you just cannot avoid the quotient rule. It's probably just easier if you use quotient rule for this rather than converting this as a power of -1 to the top and doing a product rule. So let's use a quotient rule. Remember, the quotient rule is uv, and the derivative of u times v is v u prime minus u v prime all over v squared. U is e to the 3x, so that makes u prime 3 e to the 3x. V is e to the 3x plus 4, so that makes v prime 3 e to the 3x. The 4 turns to 0. So let's go ahead and apply a quotient rule. So it's going to be v e to the 3x plus 4 times the u prime 3 e to the 3x, and then we have minus u e to the 3x times the derivative of v, which is 3 e to the 3x all over v squared, e to the 3x plus 4 squared. Now, I'm not going to do much here. I mean, there's so many things you can do. You can distribute, simplify, all that stuff. Well, yeah, might as well just go the extra mile. So let's go ahead and distribute this and this so that I get, if I multiply e to the 3x and e to the 3x, we know that we add the exponents according to the properties of exponents. A to the x times a to the y is the same thing as a to the x plus y. Okay, so it's going to be 3 e to the 6x plus 4, no, not 4, 3 times 4 is 12 e to the 3x minus 3. This becomes also e to the 6x, which leaves me with a total, well, actually these cancel. So it was worth going the extra mile. So it's 12 e to the 3x all over e to the 3x plus 4. Next problem. You have two functions being divided by each other. Now, if you're very proficient in your exponential laws, you'll know that an a to the x over a to the y is a to the x minus y. So you do not need to use a quotient rule. You simply just need to subtract the exponents, e to the 4x minus 2x, which is just simply e to the 2x. So the derivative of e to the 2x is 2e to the 2x. If you do quotient rule, you will get the same thing, just a lot longer process. Write the equation of the tangent line to the graph of e to the 2x. Well, what do you need for a tangent line? You need a slope, and you also need a point, which is already given. So all we need is the slope part, and to find slope we must use the derivative here. In the last problem, e to the 2x was e to the 2x times 2. So how do we find the derivative at this point? Plug in x equals 0. Now notice you cannot plug in y equals 1 because there is no y, so disregard the y for right now. So when you guys start doing implicit differentiation, you'll start seeing how we can plug in a whole point into our derivative. But for right now, you cannot do that. 2e to the 2 times 0 is 2e to the 0, which is 2. E to the 0 is 1, not 0. Like most students will say, they'll think it's 0 automatically. E to the 0 is not 0. My derivative at 0 comma 1 is 2. So I use my slope, my point, to put it in point slope form. And I'm done. Find the x values at which f has horizontal slopes. Okay, what does a horizontal slope mean? The slope must mean 0. Okay, and if we want to find the slopes of a graph, of a curve, then we're talking about the derivative. So we must find the derivative, set it equal to 0, and solve for any x values that would make this 0. So f prime of x is a product rule. X squared times e to the x squared chain rule times 2x plus the second term times the derivative of the first term. So let me go ahead and do this. Now that I have these very similar factors here, I can factor it out, because if you just automatically start equaling this to 0, you are going to have a hard time trying to solve for the x. So let's go ahead and factor this out. If I factor out the yellow, I get e x squared with 2x in the front plus, oh no, not plus. If I factor it out, I use parentheses, equals 0. What do I have left when I take this away? X squared, this plus 1, and we have our equation set equal to 0. Okay, so now notice, we can divide 2, that's no problem. Divide 2 to both sides, and now I have x times e to the x squared times x plus 1 squared. X squared plus 1 is equal to 0. I have 3 products that equal 0, so that means I must set all of them equal to 0 and solve for x. Let's begin with the bottom one. X squared is equal to negative 1. Well, if I take the square root of both sides, the square root of negative 1 does not exist. It's an imaginary number. In calculus, we don't consider imaginary numbers. We stop right there. There are no solutions for this little equation here. So let's go to the next part. Well, e to the x squared equals 0. If I were to solve this analytically, I can take the natural log of both sides, but I have a problem. Natural log of 0 does not exist. In fact, exponential functions that equal to 0 never exist. The parent functions never exist. It's impossible because the graph of exponential functions never touch 0, so there is no solution. So that's why it doesn't exist. Your only solution is x equals 0. Anytime you have an exponential with some variable x equals 0, your answer will automatically be does not exist. There's no such answer, there's no such x that will make this equal to 0. It'll make it approach 0, very, very close, but not exactly 0.